The static, centralized defenses that protected early mobile networks are obsolete. As physical hardware dissolves into distributed software, the boundary between the inside and the outside of the network disappears. Transitioning to 5G is a complete architectural replacement, requiring an entirely different approach to data protection. Previous generations, like 4G LTE, relied on a centralized, evolved packet core. Security was largely a matter of defending a hard external boundary. If a threat was kept outside the core, the internal network was assumed safe. This chart outlines the security foundation of LTE. Relying on a static perimeter to defend against dynamic, automated intrusion attempts mathematically guarantees an eventual breach. 5G discards that centralized model in favor of a service-based architecture. Dedicated hardware functions are replaced by interconnected software microservices running in the cloud. These microservices no longer use legacy telecom signaling. Instead, they communicate using standard web protocols, specifically RESTful APIs. Because processing is pushed to the edge of the network and relies entirely on API calls, the number of distinct entry points multiplies exponentially. Protecting this distributed mesh requires 3 distinct layers of defense: implementing security by design, enforcing zero trust at every node, and deploying AI to automate threat response. You can no longer build a wall around the data. You have to embed the security controls directly into the data pathways themselves. We start at the edge. The air interface, the connection between your mobile device and the cell tower, has historically been the primary weak point for subscriber tracking. This matrix compares 4G and 5G architectures. Focusing on identity protection, 4G transmitted the IMSI in clear text. This allowed bad actors to deploy IMSI catchers to intercept signals and track locations. 5G solves this by utilizing public key cryptography directly on the device. Before the signal ever reaches the air interface, the permanent subscriber identifier is encrypted into a temporary concealed identifier, rendering interception useless. Furthermore, 5G mandates user plane integrity protection for both control signaling and the actual data traffic, closing a gap where 4G left these checks as optional. By enforcing encryption before transmission, subscriber privacy operates as a hard-coded engineering baseline rather than a network add-on. Beyond individual handsets, this architecture supports massive, concurrent industrial applications, from automated factory floors to autonomous transit systems. This diagram illustrates network slicing, allowing operators to run multiple isolated virtual networks over shared physical infrastructure. You can see 3 distinct use cases here: low-latency communications, mobile broadband, and massive IoT, all sharing the same hardware below. Running these together requires absolute logical isolation. Compute, network, and storage resources for each slice must be separated to prevent data from bleeding across tenants. This separation enforces policy independence, since IoT temperature sensors require vastly different security than a surgical robot. Without cryptographically enforced boundaries, a localized attack on a vulnerable smart thermostat could trigger resource exhaustion, bringing down critical networks sharing the same server rack. We move inward from those virtual slices to the APIs connecting the core macroservices. This slide highlights how exposing network functions via APIs introduces web application risks into critical telecom infrastructure. Securing these pathways requires rigorous strategies, shown on the right: mutual TLS for encryption, short-lived OAuth tokens, and strict input sanitization. Pushing processing outward from the core network brings us to the physically dispersed edge nodes and millions of vulnerable IoT endpoints. As this framework outlines, edge computing nodes operate in physically unsecure environments. A cell tower is highly vulnerable to hardware tampering. Protecting these assets requires specific hardware controls, including secure boot processes and trusted execution environments to isolate workloads. Tying this all together requires a blueprint for a zero-trust architecture. Zero trust removes the concept of a safe internal network. Every single access request is explicitly verified, and microsegmentation ensures users are granted only the minimum necessary privileges. Assume the network is already breached. The engineering objective is strictly to isolate the compromise and minimize the blast radius. A distributed 5G network generates a staggering volume of daily telemetry, with millions of endpoints continuously transmitting status updates and access requests. When you are processing petabytes of data, human analysis and static rule sets become mathematical liabilities. they are simply too slow to detect novel attack patterns. Moving to predictive defense, this diagram outlines the self-healing network capability loop. Machine learning models continuously stream process live telemetry to identify anomalies and assess threat severity. The system then orchestrates containment actions, like quarantining a device, instantly, without waiting for human approval. However, this automation requires strict confidence thresholds and human-in-the-loop safeguards. An overactive AI isolating a slice due to a false positive can cause as much disruption as an actual attack. Operational security transitions from analysts staring at dashboards to machine learning models executing sub-second containment protocols. To understand how these architectural choices play out, we have to look at empirical outcomes. This slide presents two real-world case studies demonstrating what happens when 5G networks are targeted. On the right is a catastrophic failure. A telecom operator suffered an API breach when an attacker gained unauthorized access to the core using a compromised token from a third-party vendor. Because the attacker held valid API credentials, the lack of internal least privilege enforcement allowed them to bypass the perimeter and achieve total core compromise. The initial access wasn't contained. Contrast this with the success on the left. At a smart manufacturing facility, an IoT sensor was compromised due to default credentials, but because the network utilized strict microsegmentation, lateral movement was blocked. The system flagged the anomaly and quarantined the device. The initial breach occurred in both scenarios. The implementation of microsegmentation and layered controls is the sole factor that determined the ultimate blast radius. Securing a 5G ecosystem requires recognizing that the perimeter is permanently gone. In an environment driven by APIs and remote edge nodes, complete impenetrability is impossible. The true metric of a secure network is its resilience. Achieving this requires fusing distinct disciplines, combining the data protection of enterprise IT, the scale of cloud computing, and the physical safety protocols of operational technology. 5G delivers immense operational capabilities. To leverage them safely, organizations must discard legacy defenses and treat zero-trust architecture as a continuous, strategic mandate.